Let's go ahead and take a look at a question that we've seen previously to help illustrate how we can go between these different representations. So this polynomial function f includes the points given in the table below, and we want to write two distinct polynomial functions that could be represented by these points. Now, what I encourage you to do is go back, you've already looked at this problem before, take a look at it again now and see if there are anything that you would like to redo or recalibrate about the way that you went about doing this problem, and rework it again, recreating your two distinct polynomials. That way you have some ideas before we get into it. So there are a couple ways to start off, and the first way is to sort of identify the information that we know with relation to what we know we're going to need. And so if we want to write two polynomial functions, we know that we can represent a polynomial by its linear factors. We've seen that before. And that the linear factors will give us clues and help us to understand what the roots will be. Because when we have a set of things multiplied together and we want them to multiply to be 0, we know one of them has to be 0. So the linear factors are tied to the roots, and in that way we can construct polynomial functions out of these linear factors. And so if we can find the roots, we can also link our function to them. One way to think about what that is and what that looks like is to actually sketch a quick graph of the function based on the points we're given. So we know when x is equal to -1, the value of the function is 0. We know that when x is 0, the value of the function is 2. We know that when x is 1, the value of the function is 0. And we know that when x is 2, the value of the function is 0. So what information does this tell us about our function? Well, we know that each root is linked to a linear factor because a root will show up when the function is equal to 0, meaning that one of those linear factors will be equal to 0 at this particular x value. One of our linear factors will be equal to 0 at this particular x value, and same for this. So what linear factor would be equal to 0 when x is equal to -1? Not too hard to think about, right? If you have the linear factor, remember that means x is to the power of 1. If you have x plus 1, that will be equal to 0 when x is -1. Similarly, when x is equal to 1, we need the function to be equal to 0. What linear factor will be equal to 0 when x equals 1? That would be x minus 1. And similarly, when x is equal to 2, the linear factor x minus 2 will go to 0. And so those are three linear factors that are given that have to be a part of our function because we know the roots of this polynomial function are -1, 1, and 2. At this point, we might think we're done, right? Because this function is a cubic polynomial, has a leading term with a degree of 3. And so it will, we can see it will come from the left, it will hit here. We could use our thought process of how do we figure out the points in between to figure out if it goes positive or negative. But here we notice that it actually has to go positive. We need to make sure that it goes positive. And in fact, we need to do better than that. We need to make sure that when x is equal to 0, that the value of the function is equal to 2. So what else could we change about our function to make sure that is the case? Notice here that we haven't chosen specifically a leading term yet, a coefficient for our leading term. We don't have anything there, meaning that we've sort of plugged in 1 for that a sub 0 value, but that doesn't have to be the case. We can actually go through and choose the a sub 0 value so that it makes sure when I plug in 0 for x, I get an output of 2. So if we have our function f of x, and it looks like this, so far there's only one last thing that we want to choose, and that's what the leading coefficient will be. So if we plug in 0 for x, we better make sure that the end result is 2. And so if we do that, and we plug in 0, we will have, remember we haven't chosen this value yet. So we have 0 plus 1 times 0 minus 1 times 0 minus 2. And what does this need to equal? It needs to equal 2. So if we go through, this is 1, this is -1, and this is -2. So we have 1 times -1, which is -1, times -2, which will be a positive 2. So we'll end up with a sub 0 times 2 needs to equal 2. Well, this is pretty easy now. We divide by 2 on both sides, and we find that a sub 0 must be equal to 1. And so our function, f of x, will actually have a 1 in place of the a sub 0. So we can say that one function that will for sure work is f of x is equal to 1. We don't have to write it there, but I'm going to just so you remember, x plus 1 times x minus 1 times x minus 2. That is one function. But we want to write two distinct polynomial functions. Well, notice that I can create another function that satisfies all these points. It just has to be different than this one. How can I change this function? Well, I already have written a cubic, but that doesn't mean I couldn't write for example, a quartic function where I would have the same end behavior, either increasing to the left and the right or decreasing to the left and the right. And the way that I would need to do that is by increasing the leading degree, the degree of the leading term. And the way I could do that is by adding another linear factor. In other words, adding another root, or simply duplicating a root that's already here. We've seen that with roots of multiplicity too, where instead of having one linear factor of x plus 1, I could have a second linear factor, which would mean I'd be multiplying x by itself 4 times to get x to the 4th. Notice I would still need to choose my a sub 0 value. Or I could add another linear factor, which would tell me a new root that isn't currently captured in the data values that I have. That's totally up to you. And so what you're going to do now is go ahead and choose on your own. Would you like to duplicate a new root, duplicate a previous root by adding the same linear factor and multiplying it into your function? Or would you like to create a new root by multiplying a different linear factor into your function and then choosing the a sub 0 value? So make sure that your work is shown, that you've created a new function. If you and your group already created 2 functions on your own in class, then what you'll do is you'll want to come up with a new one that is different than even that function. All right, so at this point, we're ready to kind of fill in our information regarding the key characteristics of polynomials. One thing to add to the end behavior is how do we determine the end behavior for a particular function? And notice that we have a way of telling whether they're going to be different and whether they're going to be the same. But how do we know the exact direction? And we've discussed this previously. What we look at is we look at the parent function. So you'll want to use the parent function as a reference. And notice the reason you want to use it as a reference, and I'm abbreviating that REF, but you should write out reference. The reason I want to use the parent function is the parent function has a leading coefficient that is positive. If the leading term has a negative coefficient, then we just look at the parent function and reflect the end behavior over the x-axis. Next, we move on to the roots. And one quick word, we took down this information in our notes, and so your choice is either to rewrite these and add on now what we're going to add on, or go back to where you have this previously and input the new information here that we've learned. So let's go ahead and tackle now the roots, and you've seen this already, so in your mind you should already be prepared for how we're going to capture this information. The roots are linked, of course, to the linear factors. So just how we can write a polynomial in standard form, where the leading term has the highest degree, we can also factor it out into a set of linear factors. And we'll get into this more as we go on, but the factored form of a polynomial is where we have the a sub 0, the leading coefficient, factored out, and then we have written a bunch of linear factors. So instead of having x to the 5th for a 5th degree polynomial, we'll have 5 factors that when we multiply them out will give us that x to the 5th term. So we'll have x, and for convention's sake, we'll just say we're subtracting whatever that value of the binomial is going to be. So we'll call this whatever it's going to be, r sub 1 times another linear factor. Depends how many you're going to have, right? R sub 2 times however many you end up with. And if you had n linear factors here, right, and I've written this dot 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 to say that you could have as many as you want, right, that would mean that you'll have x times itself n times, which would give you an x to the n as the exponent. So this is factored form. And when we're looking for the roots, what we're doing is we're setting the function equal to 0. So in setting the function equal to 0, what are we going to notice? Think about that for a second. Well, in factored form, as I've annotated here, we have these linear factors, meaning each one is to the first power. And in finding the roots, what we're going to do is we're going to set our function equal to 0, right? That's what we're always used to. So we're going to set, I'll just call this our function f of x for now so that we can write it nice and clean. We'll set our function equal to 0. Now, what do you notice? Well, if we have this whole thing set equal to 0, that means that one of these things that we're multiplying in order to make the entire function 0 has to be equal to 0, right? So we just go through and we test each one. What would make each factor equal to 0? And then we'll simply go through and look at each of the cases. So we try the first one. What would make x minus r sub 1 equal to 0, right? And you solve for x. In this case, x will be equal to r sub 1, right? And you can think of this, we've seen this in action a lot, so on and so forth, until you've done that for every single one of the factors. So if you have n factors, you'd have n of these cases. Okay? In other words, this last one would be x minus r sub n. What will make that equal to 0? Well, that would be when x is equal to r sub n. And so these are going to be the roots. Now the last key characteristic that we have, think about it, we have the end behaviors, what's happening as you approach negative infinity, positive infinity, and the roots, where is the function equal to 0? The last thing is what's happening in between those roots. And so there are a couple ways that we can determine this, and we're going to talk about that right now. Okay, so if we are able to ascertain the end behavior and the roots, how will we figure out what's happening in between the roots? And what we've seen here is that there are a couple ways for us to do this. The first is for us to test out, using our function, if we have it, right, what is going to happen in between each root by plugging in a point that's in between them. And so a way of testing this out and organizing our work is to create what's called a sign chart. So I label my sign chart as such. It's for the function f of x. Now what I do is I mark on it, I think of this almost as being the x-axis. Where on the x-axis is the function equal to 0? Well, that's going to be at the roots. So I mark those points. Let's just mark 2 of them. Let's say this is some root, the first root that we found, and this is just the second root. How do we test what the function is going to do in between these 2 roots? Well, we plug in some x value into our function that's in between these 2 values. So you plug in some value in between, and you can pick any one that you want. And when you plug it into the function, you can determine whether it's going to be positive or it's going to be negative. The great thing about this is that once we've filled in and know the sign of our function at all parts, we can graph it easily. We can tell a lot of things about our function quite easily. So for example, if we had 2 roots that we know, and let's say we knew it was decreasing to the left, so it had to be negative, and decreasing to the right, so it had to be negative as well, here we could graph our function with ease. The function is going to be negative to the left of our root. Let's say it was positive in between, so it would cross over and be positive. And then it would come through, and here it would have to cross over again because it would be negative after. And so I can graph my function with ease. Of course, we also mentioned how certain linear factors can be repeated, meaning that that root can have a multiplicity, and how if it's got a multiplicity that's even, for example, if we have some factor, say x minus r1, was squared, that would be a multiplicity 2. And if it's an even multiplicity, we know there's no sign change, so the function would bounce off. However, if it's odd, it will cross through. And so that's a way for you to check that your function makes sense by going back and taking a look at it after you've graphed it or done whatever you need to do with it. All right, so I'm going to give you one problem to work on so that you can come in on Monday ready to go. Let's take a look. All right, here's a problem for you to try, so copy it down, make sure you complete both Part A and Part B using some of the information that we've worked on over the past week, and we will present them on Monday.